But just by itself, if I want to produce the same image that I am currently producing, I need a very high dose compared to the techniques being used now. So when you come to perform imaging on the patient, you need to think about how to best utilize the transmitted photons. I want to make the best use of the X-ray photons that have passed through this patient. So they started thinking about receiving the X-ray photons on a material. I called this material scintillator. The scintillator is the material that interacts with the X-ray photon and begins to produce light photons, or gives me light as a result of the interaction between the X-ray photon and the scintillator material. This light, which comes out as a result of the interaction between the X-ray photon and the scintillator material, will be represented or can be translated later into my image. The intensity of the light photon that comes out of the scintillator material increases as the incident X-ray photon on the patient is stronger or has higher intensity. High intensity means what? If I have X-ray photons coming from the bony area, then its intensity, of course, is there someone, guys, who can mute?
Hello everyone, I hope you're all doing well today. I would like to kindly ask if we could open the microphone for everyone at this moment. This will allow us to have a more interactive and engaging conversation. Is that okay with everyone? Please let me know if you have any concerns or if there's anything else we need to consider before proceeding. Thank you for your cooperation and understanding.
The idea in a simple area is that, in essence, I have
an X-ray source that emits X-rays, which are then received by the patient. The insulin radiation begins to undergo transmission, which is received by the image receptor. Now I want to discuss the evolution from screen film radiography to computed radiography or digital radiography. This evolution depends on how to perform imaging in the patient with the lowest possible dose, while providing options for post-processing of my image. For example, in screen film radiography, once you have taken the film and developed it using the available chemicals, the image is produced as it is, and you cannot perform post-processing or change the window level or window width. The image appears exactly as it is without any modifications. Why? Because there was something called dynamic range. In X-ray film or screen film radiography, the dynamic range was narrow. There is also a term called latitude, which we will discuss shortly. However, in computed radiography or digital radiography, you have increased the dynamic range. But in the computer or in the end, you started to increase the dynamic range. The ability to make changes and perform post-processing in the window level and window width is now available. And at the same time, you can improve the efficiency of the detection of your image receptor. Consequently, you can obtain a good image with a lower dose. This is the idea, the concept of producing images that can enhance your capabilities. Sometimes you might be provided with post-processing without detection efficiency, or it might affect the resolution. For example, the scheme for CR provides you with the best resolution because there is always a relationship between resolution and sensitivity or detection efficiency. When you significantly increase detection efficiency or sensitivity, you may find that resolution begins to decrease, or the ability to discriminate between different objects or materials with similar characteristics starts to diminish, as we will see later. Well, due to the limitations of screen film radiography, computed radiography, and digital radiography began to emerge. First, there is computed radiography, CR, and then digital radiography. The idea behind computed radiography is that in the radiology department, you have what I call CR. I have a cassette that receives my image, and then I have a reader. I start to insert the cassette into the reader, which then produces the image on the screen. In digital radiography, however, there is no need for a reader. As soon as you give the exposure and turn it on, you find your image appearing on your screen. So, what is the concept of computed radiography? Simply put, I have my imaging plate or my image receptor. I use a material called fluorobromide or bromide iodide, and I dope it with a substance called europium. Why this material? They say that bromide iodide acts like a crystal, in a crystal shape. When you apply doping with europium, it creates a defect within it, like a trap, a trapping point, or a collection point, which they call F centers that exist within this crystal. What is its function? When transmitted X-ray, photons fall on my crystal or my imaging plate, it starts to ionize the europium, converting it from +2 to +3, meaning it enters a highly oxidized state, releasing and freeing the electron. These electrons that have formed and started to experience electron trapping begin to learn and get trapped in this trapping center for a certain period, which could be hours or years. Of course, as time increases, if you take a picture of the phosphor, the image will not remain there forever. The electrons that are trapped and remain confined within your crystal will not stay there indefinitely. Over time, they will start to decay or move down to a lower energy state from what is called the conduction band to the valence band. We previously discussed the difference between the valence band and the conduction band. So, I need something to initiate the electron to exit from the trapping site and leave its position. What do? I expose my cathode to a laser beam, which will initiate this electron and release it from its position, allowing it to return to the conduction band, becoming free. It then starts to drop back to the valence band, and as it descends, it emits a light photon, which I can capture to produce my image. Here is the X-ray beam, and here is my crystal, and this is the first stage that occurs. Here is the barium iodide present, and here are the electrons that start to be trapped in the energy centers I mentioned, which were formed as a result of the doping of my barium iodide. So, what do? Here is the valence band, and here is my conduction band. When I expose it to the red laser, which is the reader, I am now doing the reading. The laser starts to give energy to the electron, allowing it to move to the conduction band, becoming free instead of being trapped. It then starts to drop back to the valence band, and the difference in energy is emitted as light photons. Great. I will start to receive these light photons This is the X-ray tube, and this is your work with the patient, and this is your work with the recording. This is the photostimulable phosphor, and this is found in barium iodide. What I talked about is the area where I perform the recording of the screen. After I record the screen, I start to make a reading using the laser. The laser here enters and frees the electron, which then emits light, photons. I begin to receive these light photons on something called a photomultiplier tube. What is the photomultiplier tube? It is something like a photodiode. On its surface, there is something called a photocathode. The photocathode converts the light photons into electron signals. After that, these electron signals undergo multiplication inside the photomultiplier tube to maximize your signal. Then, it goes to something called an analog to digital converter, and then it enters your image processing. Please pay attention to something very important. I always hear about ADC and DEC, the analog to digital converter, the signal you receive, needs to be stored in your system to be displayed. So how is this signal stored? The light photon that comes from the screen enters the photomultiplier tube and is converted from light to electron inside the tube. This electron is not just one. It represents thousands of electrons that express a single signal. The beam of electrons has a signal with a certain intensity, which depends on the transmitted beam from the X-ray that comes from the source. If the beam is strong, the intensity that reaches the photomultiplier tube will be high, and the electronic signal produced will also be high. This signal resembles a sine wave. It has a certain voltage or intensity. However, this incoming signal does not have a specific value. It doesn't tell you, for example, that this value is 10 or 20. It doesn't have a discrete value. It doesn't have a single value. It's continuous. It starts with the signal that comes in an analog form, and I want to convert it to a form that the computer understands. The computer understands any shape in digital form, which is the binary form consisting of 0 and 1. So, when you press a key, the computer does not understand the letters E, S, L, A, and M. It understands that E is a binary number, 0 and 1, a set of numbers made up of 0 and 1, which are the digital numbers. Once you give it the order, it starts converting it into numbers. These numbers are codes that it knows the meanings of, such as, Ella, and am. The same idea applies when you give it the signal. It must understand it and store it, so that in the end, the image is formed. This image is essentially a matrix, which means pixels. For example, you have a mobile phone, and I have a mobile phone. Your mobile has a camera, and this camera produces an image. This image consists of squares, and I call each square a pixel. If I am talking about it, I refer to the pixel, which contains a signal coming from the patient. How to get the color white, black, or shades of gray, and how to be the lung and the ribs and the stomach, and I see the shape of my X-ray image. Each pixel in the image contains information. Where does this information come from? This information comes from the scanning process that I perform. When I insert my cassette into the reader starts scanning in the X and Y directions relative to the cassette I have placed inside. The electrons present, and the mechanism I explained earlier begin to scan each row, moving along. Each point on this cassette represents a pixel. Each point on the cassette represents a pixel that translates how much light photon was emitted. It starts by taking this signal and determining its X and Y directions. Then, it projects this point onto the image, indicating whether the light photon here was high or if the intensity was high, which would represent this signal in black or dark color because the intensity is very high. It doesn't understand the air or the bone. It only has grayscale values. It performs normalization by taking the highest and lowest values and normalizing them, placing the highest value in black and the lowest in white. It then maps every value or signal it receives onto its grayscale. Each pixel on the cassette has been read, and its X and Y dimensions are known, allowing it to translate this onto the film. Now the signal is coming in, and I want to convert the signal from analog to digital for a reason. In order to be read and stored on the machine, something called an analog to digital converter is used. This converter takes every incoming signal and starts converting it from an analog image to a digital image, which consists of zeros and ones. The processor of the computer then interprets this, assigning a specific value to high intensity. For example, if the intensity is 50, this value is referred to as a decimal value. It then converts it to something called a binary value, which is understood by the computer as zeros and ones. By converting from decimal to binary, I have achieved a conversion from analog to digital. The computer can then interpret this value into a color and display it on my system. However, another problem arises. It tells you that in order for the image to be displayed, you need to convert it back to analog after you have stored the image and prepared it for display. It starts to process the image so that you can see it clearly. However, we are dealing with what? It is being converted and then stored, allowing you to make changes or adjustments. All of this is done, but it is converted back to analog later so that it can be shown to you properly. After reading, I need to erase the cassette, and it starts to display why it begins to erase. If there are any electrons that haven't been released yet, it starts to expel all of that and returns the cassette back to its state with all the electrons in place, and then it begins to work and operate again properly. All right, doctors, is this part clear? Good, thank God. I have finished extracting the image. No, you stored the image but did not display it. When the image is presented to you, it is an analog image. However, all the work you are doing in the background involves dealing with zeros and ones. You are working with binary and digital data. But what is displayed to you is automatically converted from digital to analog using the digital to analog converter, so you can see it.
So, the screen is made up of pixels, which are all just numbers. It all depends on the intensity that was captured. He told me that the screen itself is one thing, and the processor is another.
The processor and the manipulation process that occurs, along with the mechanism and processing of the data itself, which is binary, does not work with analog at all. If it were to operate on analog, a lot of data would be lost and distorted, leading to many problems. However, when I present the final result, it has already appeared. To display it on the screen, I need to convert it to an analog signal. It starts to show up, even if it's pixelated. There's no problem. Even if the pixel of the screen you are talking about and the resolution is normal, the image can still be fine or not. But it is preferable in display operations to see it in digital form. Why? Because analog has continuous values of intensity, while in digital, as you mentioned, you take specific numbers, discrete values. Continuous values of intensity in analog, while in digital, you take specific numbers, discrete values. This allows for more possible values to be captured during storage and processing from the signal, but it does not capture all the values. Analog is easier and faster for data transfer. For data transfer, you see it clearly without any issues, so it becomes easier for you. So, the display process now needs a digital to analog converter. Let's come here now and watch a video. This is the point I was discussing with you, that I have screen film radiography, which does not provide as many shades of gray or degrees of the grayscale as computed radiography or digital radiography. In classic radiography or film radiography, you can reach up to 30 shades of gray. Let me explain to you what I mean by 30 shades of gray. In screen film radiography, objects that are close in their densities cannot be seen as clearly as in computed radiography or digital radiography. Why? Because computed radiography uses a mechanism that transforms radiography, and you have what is called the dynamic range. The dynamic range is a concept that I will explain to you now, which is the idea that you can have a wide range of exposure that can give you different gray values or many gray values, allowing for different gray levels or varying gray levels. Here, for me, this is the bromide iodide. This compound is known for its unique properties and reactions. If it is exposed to X-rays, as we mentioned, it is what happens in the barium material. When exposed to X-rays, it undergoes a transformation similar to that observed in barium materials. It starts to Here, the speaker explains that there are two types of photostimulable phosphors. One is called conventional, and the other is called needle. The difference is that in the bromide powder, if an interaction occurs in a specific location, the light that is emitted, whether it is isotropic or directed, needs to be considered. Isotropic means that the light is emitted in all directions, which means it may not be emitted in just one direction. It undergoes diffusion and can spread in many directions. The speaker mentions that there is another type, which is more expensive, that improves resolution a bit, called needle PSP, photostimulable phosphor. This needle type is more costly because the light photons emitted during the reading process follow a specific path due to the crystal structure, allowing for better localization and dimension determination of the interaction location. Here, there is a specific track from which you can view the light photon, but the second one can be activated in multiple locations, thus reducing the need to run the imaging clip. I will turn on the sound for you.
How does everything work together? It can be broken down into more than one approach, almost resembling a combination of various methods.
Okay, Donil Forsequenzos.
In the implementation phase, the station executes the station. You can convert it to a straight level. In an excellent world, the perfected level can remain straight until it is converted. But in reality, 50% is attributed to the excellent level quickly, while the rest can be facilitated in as little as 8 hours. After the area is prepared for imaging, we take the area to the imaging course. After the area is prepared for imaging, we take the area to the imaging course. After the area is prepared for imaging, we take the area to the imaging protocol. State the diameter of the infrared laser light that determines. After the light is emitted, it is concealed using their specific phones. The light is concealed using their specific phones. Light is indeed concealed using their special phones. Light is concealed using their special phones. Light is concealed using their special phones. Light is concealed using their special phones.
This is the shape of the light photon that will appear, And this is the shape of the laser beam that will show different intensity and different wavelength, meaning different energy. That's why this is called blue light or blue visible light, which is blue. Of course, the laser is the infrared laser, which is the red shape. So different wavelengths and different intensities. The intensity of the blue light or the red. The red laser is the shape of red. So different wavelengths with different intensities. This intensity is, of course, related to the blue light or the red. The light coming from the interaction is heavily dependent on the transmitted and incident X-ray intensity at the location of the imaging plate. I was just talking about how if I have my screen or my imaging plate, and this screen contains the photosensitive material or PSP material, if its thickness is large, it would significantly affect and influence the overall quality of the image produced by the system in use at that particular moment in time and space.